All right, so some quick definitions on solution chemistry. So a solution, we talked about this a long time ago, back at the beginning of the year. A solution is a homogeneous mixture in which one substance is dissolved in another. Someone remind me, what does homogeneous mean? What is homogeneous? I know it's like totally on the screen. What is homogeneous? Same throughout, exactly. So if I have a cup of salt water and the salt is dissolved in the water, every spoonful of salt water that I pull out of this cup should be pretty much the same as all the other spoonfuls. What is the not same throughout adjective that we use for solutions? If it's not homogeneous, what is it instead? Do you remember the other word? Yeah, heterogeneous. So a heterogeneous solution is one that is not the same throughout, like chicken noodle soup. So I can take a scoop of chicken noodle soup from a bowl, I can take another scoop from the same bowl, and this one might have one noodle and a piece of chicken, but that one has a carrot and two noodles, not the same, it's heterogeneous. In our solutions, we have a couple components that you need to have the definitions known for. So solute and solvent. Solute is the substance that is being dissolved. The solvent is the substance that dissolves the solute. So if I have my solution of salt water, my homogeneous solution of salt water, tell me which one is the solute, which one is being dissolved. The salt, exactly. So the salt is the solute, which means that the water is the solvent. The water would be the solvent because it's dissolving the salt, which is the solute. So far, so good. Easy peasy start. Good. So this process of dissolving is pretty cool chemistry, and also a little bit of physics. So there's some magnet-like attractions going on in here. So something like salt, sodium chloride is normal old table salt. Sodium are these positive sodium ions, and then these negative guys, these are the negatively charged chloride and ions. Water is what we call polar. It has both a negative side and some positive sides. Water is polar, it has a negative side and some positive sides. The negative oxygen side has more electrons floating around it, which is why it's negative. These positive hydrogen sides of water, they have fewer electrons, which makes them more positive. So the positive side of water, where the hydrogens are, is attracted to the negative chloride anions. There's a little force of attraction, like little magnets here. At the same time, these positive sodium cations are attracted to the negative, opposites attract, to the negative oxygen sides of waters. And so we end up with all these little pieces of the salt being totally surrounded by water. So you can see the water, all those hydrogen pieces of the water molecules all around the chloride ion. We end up with these lovely little layers of water, bubbles of water, surrounding all the pieces of the salt, which allows the salt to break into those little pieces, and the pieces float around in the water because they're surrounded by the water. Because with little magnets, they're attracted to each other. I have a video that I tried to add. I don't know if it's going to work. We shall see if technology has been conquered today or not. Fingers crossed. Oh, I think it's working. And there is no sound. So if you're like, I don't have any sound, I don't know why they didn't add sound. Read the words. Good? Yes, good. Makes sense. Yeah. It's kind of pretty, right? Anybody in French kind of enjoy the bilingual piece of the video? So in biology, you definitely should have learned something about water being polar. The question was, did we learn this last year in biology? You probably learned at least a little bit about water being polar. It is essential to life. Without water being polar, living things would not do very well. Because water is polar, we're able to transport blood and sugar and all kinds of cool stuff around our bodies. If water were not polar, plants wouldn't be able to suck water up out of the roots and into their leaves. So you probably talked about water being polar in bio, at least that part of it. All right, so we're talking about things dissolving. Does everything dissolve? It doesn't. How do we know if it dissolves or not? We have a table for that. We've looked at this before. What were we learning about when we used this table before? Do you remember? Such with a P. Hold on. Anybody remember what reaction we had that led to an insoluble solid product? Maybe yes, maybe no, such as P. Precipitate. Yes, so precipitation reactions. Yes, good. So precipitation reactions are those that result in an insoluble product. So how do we know if something will dissolve in water or not? We look at its solubility. We have a table for that. So let's review this really fast. So sodium chloride, soluble or insoluble? We're usually going to look at the anion part of the compound. So I see chloride, I find chloride down here. This chloride is attached to some sodium. It should be soluble, it should dissolve in water, but let's make sure that sodium is not one of our exceptions. So sodium chloride is not silver or lead or mercury, so this guy is soluble. How about ammonium bromide? Ammonium bromide. I have ammonium here. Oh my goodness. If I draw too small, the PowerPoint gets super sad. Ammonium is here. It is soluble, except it's always soluble, so this guy's definitely going to be soluble. Potassium nitrate. Here's nitrate. Soluble or insoluble? Soluble for sure. How about lead 2 iodide? Lead 2 iodide. The iodide is here. It's soluble, except if it's with lead. So is this guy soluble or insoluble? Soluble or insoluble? Insoluble. This will not dissolve in water because it's one of the exceptions. How about magnesium hydroxide? Hydroxides are down here. So hydroxides are insoluble, except if it's with ammonium or alkali metals. Remember, those are the group 1 metals in the periodic table: lithium, sodium, potassium, calcium, strontium, and barium. So magnesium hydroxide, soluble or insoluble? Soluble or insoluble? What do we think? Soluble or insoluble? Which one? Soluble? Actually insoluble. So because magnesium is not one of our exceptions, Magnesium is not in that list of exceptions. Magnesium is going to be, magnesium hydroxide will be insoluble. What about calcium hydroxide? Should also be insoluble, except when hydroxide is combined with calcium, it is actually soluble. Good? Maybe good, kind of, sort of. All right. So let's say that I've got some sodium chloride, some salt. I know that it should dissolve, and I want to make it dissolve faster. I want to speed up that rate of dissolving. What could I do to the size of the salt crystals, the surface area? Do you think a big chunk of rock salt or tiny little crystals of salt? Which one will dissolve faster? Tiny pieces, for sure. So if we have more surface area, which usually means little pieces, we're going to dissolve faster. How about temperature? I throw some salt in the water. Should I keep it cold water or hot water? Which one is it going to dissolve faster, cold or hot? Hot water? Yeah, so if I heat up the water, higher temp is going to mean a faster dissolving. What if I'm making Dr. Pepper and I want to dissolve carbon dioxide in the water? Should I heat it up? What happens to Dr. Pepper when you leave it in a hot car? Does the carbon dioxide stay dissolved? Will the carbon dioxide bubble stay dissolved in the hot car, or does it go flat? It goes flat, yeah. So higher temperature, faster, if it's a solid that we're trying to dissolve. But oddly, a lower temp is better if I want to dissolve gases, carbon dioxide in water, or oxygen, dissolved oxygen in water. The lower the temperature, the better. And so this is actually a little bit of a concern for many biologists as we look at the potential impacts of climate change. As the oceans get warmer, that's going to mean less oxygen dissolved in the ocean water, which means less oxygen for the fish to breathe through their gills. And so there are some concerns about how things are going to survive in water if the water on Earth gets too warm. There won't be enough gases, carbon dioxide and oxygen bubbles dissolved in the water to support life in the water, which is a problem because we rely on that water life quite a bit. All right, one more, agitation. If I'm trying to dissolve some salt, should I just pour the salt in and leave it alone, or should I stir? Leave it alone or stir? What's the better way to dissolve the salt? Stir, yeah. So, oopsie, more agitation, stirring or shaking or otherwise causing things to move around a little bit is going to be more and faster dissolving if it's a solid. Tell me what happens to the gas bubbles in your Dr. Pepper if you shake up your can of Dr. Pepper before you open it. The bubbles escape really fast, right? So we actually want less agitation, less shaking and stirring if we're talking about gases. The other thing that gases really like is pressure. So when we keep the top on the Dr. Pepper, we're keeping the pressure inside the bottle. And so that carbon dioxide stays dissolved pretty well in our soda. But if I take the top off and I leave it off, that pressure is a little bit increased. We have higher, well, we decrease the pressure on the inside. We release the pressure to the outside, which leads to fewer gas bubbles. We want to keep the pressure in. High pressure inside the bottle is going to better dissolve our gases. All right. So a couple more vocabulary words, and we're going to do some math. So hopefully you have your calculators ready. Saturated solutions. Solutions that are saturated have the maximum amount of solute dissolved in them. Unsaturated probably means what then? Saturated has the maximum amount of solute dissolved. What do you suppose unsaturated would be? What's unsaturated? If saturated is the maximum, unsaturated is less than the maximum. Exactly. So, oh, I lost my pen. Less than the maximum is dissolved. We have space to dissolve some more. But if the solution is saturated, there is no more space between the water molecules for more salt crystals to dissolve. So this solution, I've added 30 grams of salt water, well, salt. I've added 30 grams of salt to the water to make salt water. The salt is beautifully dissolved all throughout the water. This is unsaturated because I could add more salt. I could get more salt to dissolve. But if I add 40 grams of salt to that same amount of water, now I have 4 grams of salt that settled to the bottom of my beaker because this solution is saturated. I have filled it with as many little pieces of salt as will fit. The maximum grams of salt that we can dissolve in 100 milliliters of water is 36 grams. If I add any more than 36 grams, the extra is just going to settle to the bottom of the beaker. Good? Good. All right. So when we are talking about saturated solutions, unsaturated solutions, a little closer to saturated, not very saturated at all, sometimes it's nice to have numbers to kind of back up just how much stuff is dissolved in our solution. This brings us to the idea of molarity. So molarity is our most commonly used way to measure, calculate concentration of solutions. It is the measurement of the concentration. So if we say something is very concentrated, it has a high molarity. If something is not very concentrated, if it is very dilute, it has a low molarity. Our formula is moles of the solute divided by liters of the whole solution. You do not have to memorize it. It's on your handy dandy periodic table. So under solutions, which is on that first page, almost maybe the bottom third of that first piece of paper, you'll find your solutions formula. Molarity is the one that we're going to talk about for the next chunk of time. And we're going to also look at this one a little bit later. So molarity is moles of solute divided by liters of solution. We use this big M, molar, as an abbreviation for molarity, but it's still going to be moles divided by liters. Moles of the solute divided by liters of the whole solution. So let's go ahead and practice. If I have 2.3 moles of sodium chloride dissolved in 0.45 liters of my solution, what is the molarity? What do I need to do with my handy dandy calculator? Molarity is moles divided by liters. What's my moles? 2.3 moles divided by, what's my liters? 0.45 liters. Handy dandy calculator, we're going to do a 2.3 divided by 0.45, and I get 5.11111. What do I need to check? Sig figs. Perfect. How many sig figs should I keep? 2, exactly. So I've got 2 here, and I've got 2 here. So I'm going to keep 1 and 2. That 1 is going to do what to that 1? Nothing. It's going to stay the same. So 5.1. We could say 5.1 moles per liter, or a nice shortcut, 5.1 molar. That big M represents moles divided by liters. Good? Let's do this one. I've got 1.2 moles of calcium carbonate in 1.22 liters of solution. Molarity again is 1.2 moles divided by 1.22 liters. Calculator, 1.2 divided by 1.22. Gives me 0.9836. Lots of decimal places. How many sig figs do I get to keep for this one? 2, yeah. So this guy has 2 sig figs. This guy has 1, 2, 3 sig figs. We need to pick the smaller of the givens, which is 2 sig figs. I'm going to keep 1, 2. That 3 does what to that 8? Stays an 8. 0.98 molar is this guy's concentration. 5.1 molar was that guy's concentration. Which one is more concentrated? Which one has more stuff dissolved in it? Number 1 or number 2? Which one is more concentrated? Number 1, for sure. More than 5, less than 1. This guy is definitely more concentrated, a lot more stuff dissolved in it than this guy. This guy's a lot more water. This guy's more stuff dissolved in the water. All right, 98 grams of sodium hydroxide is dissolved in 2.2 liters of solution. Molarity is moles over liters. 98 grams divided by 2.2 liters. Anybody going lengths? That's wrong. Yeah, we gotta convert our grams to moles. Be careful, make sure that you read really carefully. If you've got grams, you cannot just throw it into the equation. You need to turn grams into moles. So let's do that real quick. I've got 98 grams of sodium hydroxide. What's my formula for sodium hydroxide? Sodium is Na. What's hydroxide? Not just an H, but OH. OH. Hydroxide is OH. The charge of -1. Sodium has a charge of +1. Luckily, those balance out. So I've got 98 grams of NaOH, sodium hydroxide. To convert that to moles, I've got grams on the top. I'm going to put grams on the bottom. Grams goes here. Moles goes on the top. 1 gram, 1 mole is how many grams? Let's add it up. Sodium is 22.990. Plus oxygen is 15.999. Plus hydrogen is 1.008. Grand total of 39.997 grams. So we can cancel out grams top and bottom. Gone and gone. What are we left with? 98 times 1 divided by 39.997 gives us 2.45. Lots of decimal places. Moles of sodium hydroxide. So when I go to my formula, I am not going to use that gram number, but instead we're going to use our mole number. How many moles, how many liters? 2.5 divided by 2.2 gives us a 1.136363. Lots of decimal places. How many sig figs are we going to keep? 2. 1, 2. That 3 leaves that 1, a 1. Final answer, 1.1 molar. Good? Good. All right. This one, I've got 1.2 grams of hydrochloric acid and 25 milliliters of solution. Got to turn my grams into moles. 1.2 grams of hydrochloric acid. What's our formula for hydrochloric acid? What's our formula for hydrochloric acid? HCl. Perfect. Whoopsie. HCl. So grams on the bottom, so I can get it to cancel out. Convert my grams to moles. Put moles on the top. Hydrogen is 1.008 plus chlorine is 35.453. Gives us a grand total of 36.461 grams per mole. That cancels out grams top and bottom. We are left with just moles. 1.2 times 1 divided by 36.461 is 0.032911. Lots of decimal places. How many sig figs do we keep? 2. Good. Remember that these zeros don't count as sig figs. They are just placeholders for those decimal places. So I'm going to keep 1, 2. That 9 is going to do what to that 3? Sorry, that 9 is going to do what to that 2? Turn it into a 3. Good. So 0, 3, 3 moles of HCl. Good. So now I can use my molarity is moles over liters is 0.033 moles over 25 milliliters. Uh-oh. What's the problem now? It's in milliliters, not liters. So I have to do another conversion. I have to get rid of my milliliters and turn it into liters. 25 milliliters. How many milliliters in a liter? How many milliliters in 1 liter? 1,000. 1,000 milliliters in 1 liter. So 25 times 1 divided by 1,000 is going to give us 0.0025 liters. 25 divided by 1,000. 0.002. Wait, that's too many O's. 0. Hold on. Decimal place should be here. 0.025, 0.025 liters. So back to our formula, 0.33 moles over 0.025 liters. We can finally do some division. 0.033 divided by 0.025 gives us a 1.32. No more decimal places. Do I have the right number of sig figs? Nope. How many sig figs do I get to keep again? Just 2. So what happens to just 1.3? Exactly. Hold on, my pen turned off again. Final answer, 1.3 molar. Good? Not terrible? Not too terrible. After stoichiometry, like nothing is that terrible, right? So let's say that I want to make some potassium carbonate solution. I need to know how many grams of potassium carbonate I need so that I can make 200 milliliters of a 2.5 molar solution. This is a little bit different, but also the same as the last couple questions. So how many grams? This is what I'm trying to find. I know that I've got 200 milliliters. What do I have to do with my milliliters? Turn it into liters. Good. So I'm going to turn my 200 milliliters into liters. You know that there are 1,000 milliliters in 1 liter. So 200 times 1 divided by 1,000 gives us 0.2 liters. I have a 2.5 molar solution. My formula is molarity equals moles over liters. I know molarity, so I'm going to plug that in right there. 2.5 molar equals, I know liters, I'm going to plug that in right there. 0.2 liters. What I don't know is grams. Should I put grams here? Should I put grams here? Not yet. What needs to go here first? Moles, exactly. So I'm going to solve for my moles here. How do I solve for x? So think some lovely algebra. If I've got this x, 2.5 equals x divided by 0.2, how do I solve for x? Multiply both sides by? Perfect. Multiply both sides by 0.2. Oops, I put the decimal place on the wrong side of the 2. Oopsie. John, you need to go? Baseball things. So 0.2 times 1 divided by 0.2, this cancels out. 2.5 times 0.2, 2.5 times 0.2 gives us x equals 0.5 moles. Do we have our answer? Now we need to turn our moles into grams. Yep, my question. So we don't have to divide. because we multiplied instead, right? So we multiplied both sides by 0.2. So that canceled out. We have x equals 0.2 times 2.5, which equals 0.5. We have our mole number. That is not yet our gram number. To turn our moles into grams, I need to figure out the molar mass of potassium carbonate. To figure out the molar mass of potassium carbonate, we need to write the formula for potassium carbonate. Potassium is K. It has a charge of +1. Carbonate, what in the world is that? It's been a while since we've done nomenclature. Carbonate, what is the formula for carbonate? Perfect. CO3 with a charge of -2. CO3 with a charge of -2. So I have a +1 charge and a -2 charge. Is that a match? No. How do I fix it? How do I balance those charges? 2 potassiums. Perfect. So K2CO3 is going to be our formula. Potassium, finding our molar mass. Potassium is 39.098 times 2. I've got 2 of them. Plus 1 carbon is 12.011. Plus 3 oxygens. Oxygen is 15.999. Oh my gosh. I am struggling to push buttons on my calculator. Okay. So 2 potassiums, 1 carbon, 3 oxygens gives us a grand total of 138.204 grams per mole. What do I do with that? Should I multiply or divide? So I want to turn these moles into grams. This is the molar mass. I'm right here. We are going to multiply by the molar mass, exactly. Because I have moles, I want to get rid of moles. I'm going to put moles on the bottom. I'm going to put the molar mass, the grams, on the top so that my moles, top and moles bottom, cancel out. So 0.5 times that answer, 138.204, gives us a grand total of 69. Lots of decimal places. I only get to keep 1 sig fig. So how many grams am I going to measure out? 70. Good. 70 grams of potassium carbonate dissolved in 200 milliliters of water will give us a solution with a molarity of 2.5 molar. Good? It's a lot of algebra, right? Yes, it is. Okay. So now I want to know, similar, but slightly different. So now I want to know how many liters I can make of this solution if I have 75 grams of lead 2 oxide. So I'm still going to use that same formula in the end. Molar equals moles over liters. I have my 0.75 that I can plug in for molar. Do I know my moles yet? I don't. I have to turn my grams into moles, but then I can plug this in. Do I know my liters? Nope, that's what we're trying to solve for. So X liters is what we're going to solve for in the end, but I can't plug in this value yet, so I have to turn my grams into moles. I have 75 grams of lead 2 oxide. How do I write the formula for lead 2 oxide? What's that going to look like? What's my symbol for lead? Pb, perfect. What's the charge of lead? 2. 2, good. Oxide is oxygen. Oops, what's the charge of oxygen? Perfect. They balance out. We don't have to do anything. So we have 75 grams of PbO. which sounds like PB&J, but PBO you would not want to eat. It would be bad. Let's turn our grams into moles by figuring out the molar mass of PBO. So lead on the periodic table is 207.2. 207.2 plus oxygen is 15.999, 15.999. We end up with a grand molar mass of 223.199 grams per mole. Grams on top and grams on bottom cancel out. We're left with moles. 75 times 1 divided by 223.199 gives us 0.3360. Lots of decimal places. How many sig figs do I get to keep? 2. 2. 1, 2. That 6 does what to that 3? Rounds it up to a 4. So 0.34 moles is what I'm going to put in my formula for moles. 0.34 moles. So now I need to solve for this x. I'm going to get rid of the unit labels because I think sometimes it's easier to see the algebra if you get rid of all the extra labels. So we have 0.75 equals 0.34 divided by x. The most common mistake we make doing this algebra, lots of us are going to want to divide by 0.34. That's a great possible plan, but it is not the final answer. If I divide by 0.34, that cancels out. Divide by 0.34 on this side, I have 0.75 divided by 0.34 is a 2.2. Is that equal to x? Look, where is x? Did I just solve for x? No, I solved for 1 over x. X is still in my denominator. How do I get x out of the denominator? What if I did that? 2.2 over 1 equals 1 over x. How would you solve for x now? Cross multiply and divide. Perfect. So x times 2.2, 1 times 1. Divide both sides by 2.2. X is going to equal not 2.2, but 1 over 2.2. 1 divided by 2.2. And our final answer is 0.45454545. We're going to keep 2 sig figs. This is the number of liters of that solution we can make. I am recording this. Yes. It was going okay until the algebra started, yes? Got it. Yes. All right. Let's do something different for a couple slides. So molarity, what we've been doing the last couple slides, this is what we are going to, that's the concentration that we are going to use 99% of the time in our class. But there are other ways to calculate concentration. And so I wanted us to just know about these other things that we can use to calculate concentration, because sometimes in the real world, outside of chemistry class, these are the things that you see instead of our molarity. So, similar but different, instead of molarity, there's also molality. Molality. So molality, we have that same moles of solute, but instead of liters of solution, instead of liters of solution, we have kilograms of only the solvent. Moles of the solute divided by kilograms of the solvent. So the molality, if I have 2 moles of sugar dissolved in 10 kilograms of water, what would be the molality? Moles over kilograms. How many moles did we have? 2 moles divided by how many kilograms of solvent? 2 over 10, what does that equal? Perfect. So 0.2 molality, whoa, that was a weird M. 0.2 molality would be the concentration, not in molarity. Good? These guys, you don't have to memorize these. These will not pop up on quizzes or tests. No panics about memorizing. I just wanted you to know because they exist in the real world. Parts per million or billion or anything. So parts per million, parts per billion. Now we're looking at mass divided by mass. So we had moles and liters and moles and kilograms. Now we don't have any moles. Everything's just mass. So grams of the solute, the stuff that's getting dissolved, grams of the solution, everything that is making up that substance. But to make it parts per million, then we multiply by 1,000,000. What if I wanted it to be parts by billion? Parts per billion, what would I do? Instead of multiplying by 1,000,000, we would multiply by 1,000,000,000. Exactly, easy peasy. So this we can change depending on if it's million or billion or whatever. So we know that lead in drinking water is really bad. No amount of lead is safe, but we're like, it's not a cause for concern. If it's under 5 parts per billion. If we have less than 5 parts per billion lead in the drinking water, we're like, not that bad. It's bad, but it's not that bad. So, I don't know if you guys have read about Flint, Michigan. They have had some serious struggles with their water for like 7 years now. We have not fixed it yet. Friends, this is America. We should be able to fix the water supply for our citizens. And yet, Flint, Michigan is still not able to drink water out of the faucets. 10% of the homes tested in Flint, Michigan, there were more than that many grams of lead in every liter of water. I want us to figure out what that is equal to in parts per billion so that we can compare it to that number 5. So grams of solute, this is my grams of solute point. 1, 2, 3, 4 zeros, 1, 2, 3, 4 zeros, 27 grams of lead dissolved in every liter of the water. So what's kind of cool about water, it has a density of 1 milliliter is 1 gram. So if I have a liter of water, how many milliliters do I have? I have 1 liter of water. How many milliliters of water do we have? Let's see it. Chat. Chat says, Caroline, I'm just seeing your question. When we get to the end, remind me and we'll go back and we'll talk about that. Good. How many milliliters in a liter? It is 1,000. Perfect. So if I have, hold on, my pen just turned off. If I have 1 liter of water, I have 1,000 milliliters of water. The density of water, 1 milliliter, has a mass of 1 gram. So if I have 1,000 milliliters, how many grams do I have? 1 milliliter is 1 gram. So 1,000 milliliters will be 1,000 grams. Exactly. So you have 1,000 grams of water and 0.000027 grams of lead. I want to turn that into parts per billion. So I should divide my grams and then multiply by what number? Billion, exactly. There's 1,000, there's million, there's billion. So, 0.000027 divided by 1,000. That's a teeny tiny number, 2.7 times 10 to the minus 8. That's not very much lead at all. times 1 billion, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, 27 parts per billion lead in the water. Good, bad, or like serious, tragic, human horror? Friends, it's so bad. Like, we really need to fix the water in Flint. It's time. It's past time. It is not safe. It's not safe. It's a American city, and there's lead in the water. All right, that was my other soapbox for the day. Another way that we can calculate concentration is with percents, parts over whole. So we can do percent by mass, the mass of the part that's the solute divided by the mass that is the whole solution times 100. Or we can do volume if we're like dissolving liquids in other liquids. We can calculate the percent that's just the solute divided by the entire volume of the solution. So let's say that I take 25 milliliters of acid and I dissolve it in 75 milliliters of water. Percent acid by volume. Well, the volume of my solute is that 25 milliliters of acetic acid of vinegar. What's the volume of my whole solution? This is a little bit of a trick question. What's the volume of the whole solution? Is it 75? Or is it 100? Why is it 100? Because we put those 25 in those 75. And so now our new total is 100 milliliters of solution. The combination of that 25 milliliters of vinegar added to 75 milliliters of water makes a grand total of 100 milliliters altogether. Times 100 to turn it into a percent. This is math that I can do in my head, my friends, even on a Thursday afternoon. What's this percent? 25 divided by 100 times 100. 25%. Good? Who's having fun? So much fun. All right, let's talk about another definition. So we're talking about all these concentrations. We can have concentrated solution. I can measure the concentration by dividing moles by liters. When I buy chemicals to have here at school for us to do labs, I usually buy very, very high concentrations, very concentrated solutions, because I can pack a lot of chemical into a smaller space. When I buy hydrochloric acid for here at school, I usually buy it in 12 molar hydrochloric acid. 12 moles of HCl dissolved in every liter of that solution. This will melt your face off. When I open my bottle of 12 molar HCl, I have to do it in the hood while I'm wearing gloves and an apron and goggles, because just the vapors that come out of this bottle could hurt me badly. So we, in our class, we never, ever, ever use 12 molar. I usually add water to get that 12 molar down to like 1 molar, which is like stomach acid, not melt your face off, still a little bit of a burn, but not melt your face off. So this process of adding water to our solutions to make them less concentrated, we call that a dilution. We're making our solutions more dilute. I've got some stuff, I add more water, and now it's not as concentrated, it is more dilute. We can calculate the new molarity with this lovely ratio of volumes and molarities. So I'm going to use this formula, V1, M1, V2, N2, V1, M1, V2, N2, and that's going to allow me to calculate how strong is my solution after I add some water to it. So if I have 250 milliliters of a 0.1 molar lithium acetate solution, and I add water so that the new volume is 750 milliliters, I want to know what is the new concentration. I'm going to use V1, M1, V2, M2. This volume is my V1. This molarity, that concentration, is my M1. This new volume is my V2, and M2 is what I'm trying to find. So V1, M1, V2, M2. V1 is 250 milliliters. M1 is 0.10 molar, equals V2 at 750 milliliters. M2 is, I don't know yet. How do I solve for M2? Algebra-wise, how do I solve for M2? So close. Yes, we are going to multiply those guys. Hold on, my pen turned off again. We are going to multiply those two. 250 times 0.1 is going to give us 2.5 milliliters times molarity. I now have 750 milliliters times M2. So close. So we're saying here subtract, which is oh so close, but these guys are being multiplied. Yes. Yes. Sorry, I missed that whoopsie. I missed that decimal. Sorry. Yes, 25, not 2.5. So our solution is, because this is being multiplied, we're going to divide by 750 milliliters on both sides of the equal sign. So 750 cancels out. All we're left with is M2, which is good because that's what we're trying to find. M2 is our new concentration. 25 milliliters times molarity divided by 750 milliliters. What happens? Milliliters on top and milliliters on bottom, they cancel out. What am I left with? Big M. That's good because I'm trying to find molarity. Now we can do the calculation. 25 divided by 750 is going to give us 0.03333, all the threes. How many sig figs should I keep? Not 3, but 2. Yep. So I don't need that one. I don't need that one. 0.033 molar is our new concentration. Good? Good. All right. Let's do another one. What if I have 240 milliliters of a 0.5 molar sodium bromide solution? I add, be careful here, if I add 560 milliliters more water to it, what will be the new concentration? So this one is our V1. This one is our M1. Is 560 V2? Is 560 the V2? No, why not? Exactly, I added that to that. So our V2 is actually going to be 340 plus 560, which is how many? 900 milliliters. Perfect. Now I can go ahead and use my formula. V1 M1 equals V2 M2. V1 is 340 milliliters. M1 is 0.5 molar. Set that equal to V2 is 900 milliliters. M2, I don't know yet. We're going to divide both sides by 900 milliliters. 900 milliliters, top and bottom, cancels out. Over here, all we're left with is M2, which is what we're trying to find. Over here, milliliters on top and milliliters on bottom cancels out. Calculation-wise, 340 times 0.5 divided by 900 gives us 0.1888 all the 8s of the world. My label is big M because milliliters cancel that. How many sig figs do I get to keep in this one? It is only 1. Perfect. Because I've got 2 here, but I only have 1 here, and I have to go with the fewer. So I'm going to just keep 1. 0.1, except that 8 does what to that 1? 0.2 molar is my new concentration. Good? Good. If I leave 750 milliliters of a 0.50 molar sodium chloride solution uncovered on a windowsill, 150 milliliters of the water evaporates. What's the new concentration? How am I going to do this one? 750 mils. Is that an M or a V? Yeah, it's V1. What's this? M1. Perfect. Is this V2? No. What is V2? Perfect. M2 is 750 minus 150 because we lost that much water. How much is left? Only 600, exactly. This is our M, sorry, not our M2, our V2, our V2. So now we can do V1 M1 equals V2 M2. V1 is 750 milliliters. M1 is 0.50 molar equals V2 is 600 milliliters. And M2, I don't know yet. Divide both sides by 600 milliliters. That cancels. Mils on top and mils on bottom also cancel. We have 750 times 0.50 divided by 600. And our new M2 is 0.625 molar. Sig figs, how many do I get to keep? 2, exactly. All of our givens have 2. We're going to keep 1, 2. That 5 turns that 2 into a 0.63 molar is our final answer. Good? Good. All right. We have 20 minutes, so we are going to skip the simulation time. I'm going to go ahead and show you on the screen what the simulation looks like, because if you are struggling with what even is happening, that might be a really nice way for you to have an animation to kind of support what you're doing. We will try to make time for the simulation next class instead. I'm going to publish problem set 6.1 right now, so you can start it if you want it. There will be a quiz at the start of class on Tuesday. So Tuesday's class, 1:45, take the quiz. 2 o'clock, jump into Zoom. We'll start our next lesson. And there's no school tomorrow. Who's excited for that? Good. All right.